Hi everyone, my name is Aryan Seth. I'll be taking today's lab on neural networks. Please let me know if you can see my screen in just a second. Yeah, I hope my screen is visible.
Yes, sir.
Okay, so today's session is essentially on the basics of PyTorch and building a simple neural network. We won't be going very deep into the theory. I believe that will be covered in the lecture sessions. Today is just going to be on implementation and the different like short tricks you can use on PyTorch. Obviously, a lot of the things you can learn from the documentation because that's going to be far more comprehensive than a 1.5 hour session. Also, please note at the end of the session, you will be shared a Google Form link which will have a short quiz, about 4 questions, and you'll get about 5 minutes to do that. So to start with, today's session. So essentially, we'll be doing this on Google Colab, and it's good to know that if you want to run a GPU, you have to have the GPU accelerator set on Google Colab. Otherwise, CUDA access will not be like given to you, and you won't be able to use that. So you'll only be able to use CPU training. So so Colab comes inbuilt with PyTorch and NumPy. A lot of the basic libraries that you'll be using, it already comes pre-installed with that. So we don't need to pip install it again. So you can simply do import torch and import NumPy, and it'll work. Now, the fundamentals, so like the same way how NumPy has arrays and Python has lists, Torch has something called tensors. Now, the main difference between a NumPy array and a NumPy and a Torch tensor is that Torch tensors work on both CPUs and GPUs. Uh, Other than that, there's no real difference. You can pretty much use them the same way. So if you had to make your first tensor, so I'll add text here. We'll start by creating the standard Python list. We'll try it. So this is going to create a tensor of the same type as the array and the list, or the list that was specified. You can do this in NumPy as well. It'll give you the same output. You can initialize your tensors in a variety of different ways. So I'll do it from NumPy just to be to show. Put NumPy as NP. So let's start. And x underscore NP is this will again create another tensor. So you can initialize tensors in a couple different ways. So if you had to create a tensor which was filled with just one, so you can write torch dot um, ones underscore like underscore data. Yeah. So this is going to create an array. This is going to create a tensor of the same shape as x underscore data, which was 2 comma 3, and it'll create it just with one. Similarly, you can do one with x dot zeros as well. Um, so you can also create a shape array, which is like let's say 2 comma 3. Just giving you an error. and I can create a random tensor. This is going to give you a bunch of random values between 0 and 1. Again, very similar to NumPy in terms of the kind of functions you'll get. Similarly, you can have between zeros and others. One of the interesting ones is torch.linspace, which creates a linear space between, let's say, two random numbers, so 1 and 15, and with a spacing of 1. So this will create, this is just like one input, right? So that's essentially, so this is the number of steps, which this means the number of outcomes you'll get. So if I make this 3, you'll get 3 outputs, which are all equally spaced. And if I make this 5, similarly, you'll get more values out. So that's essentially how you can sort of deal with, like create your tensors. Unlike NumPy, you can't create an empty tensor and append values to it. A tensor needs to be defined in shape. It's like a tuple. It's immutable of sorts. Are there any questions up until here? No. Okay. So if I created, so now we'll work on tensor operations. Essentially, how you can create, how you can like work on tensors. So addition, subtraction, multiplication, again, remain roughly the same as compared to NumPy. The only difference comes in with multiplication, where the notation is slightly different. There's no other real difference. I'll just copy this again here. And as you will see, this will give you the second value, which is point. Yeah, it will give you 8, right? Because that's the third value here. Similarly, if I had to create another tensor and add it, I can write plus b and give me the additional values. But this isn't working because the size of the tensor is must match. So I have to make this 5 and then we'll add again. So this is going to give me a standard output. Similarly, if I wanted to multiply two matrices, if I wanted to multiply the standard way, which is the standard multiplication, we'll have to do a at b. And this will give you a single value because it's matrix multiplication, row times column. If I wanted to do an element-wise multiplication, I would do a star b, which is going to give me 5 outputs because it's element-wise instead of net multiplication. Similar Python functions also remain the same. If I wanted to look at only a certain part of the array, I would do and I 2 colon, which is going to give me all the values from the second second index onwards. Now for matrices, for tensor matrices, I'll have to look at giving it a certain shape. So if I do if I define a matrix torch.rand 3, 3, and I have to print torch, I have to print a as well. This is going to give me a 3 by 3 matrix with random values. And again, if I just do this is going to give me a single value because there's only one left. So apart from the standard additions and subtractions, reshaping is an important part of tensors, also an important part of NumPy, but you can use them here as well. It's going to be important when we're working on building a standard neural network because we'll be compressing and we'll be reshaping an image to a linear 1D array. So you can reshape a 10 element 1D array to a 5 comma 2 5 rows 2 columns array as well. Similarly, you can do this with anything. And if I had to show you another, if I had to show you one more thing, I could show you a view 5 comma minus 1, and it will see that it has to fit the other. So if it has 5 rows and 10 elements, it needs 2 columns, right? It won't get rid of any of the element values. And similarly, if I think if I throw, no, it won't throw an error. It might. Yeah, it'll throw an error because it won't get rid of any of the values unless you explicitly remove them and then uh, run torch.view. So -1 will allow it to figure out the second set of values on its own and essentially make sure that it won't throw an error if you need 5 rows and don't want to figure out how many columns because the data is slightly more complicated. You can just leave it like that. Now for concatenation, you can. So if I want two tensors and I want to add them, so I do torch is torch dot rand. I'll change it to a standard runtime now because it might not let me do that later. It might not let me use it later. So this is torch is not, yeah, the runtime changed. So I'll have to start again. Right. So this is going to horizontally concatenate all the both the tensors. If I do dim equal to 1, it'll do it vertically, which means it'll just add each one into the same array as before. Does this is everyone clear up until this point? Okay, I'm going to assume that is the case. Now I'm going to leave in place operations for now, and I'll come to autograd. So as we know, the main, like the basic concept behind neural networks and the way they work is gradient descent or some type of optimizer, right? Which essentially means that you need to be computing gradients across a variety of different tensors, and PyTorch allows you to do that in a very simple way called autograd, which will essentially compute and store matrices in memory for you in case you need them later on, instead of computing gradients every time you need to make a calculation. Why is this important? It essentially reduces the net amount of memory you need for standard matrix for standard gradient calculations, and it does so. Autograd works. I'll write it here. Autograd works by creating an directed acyclic graph which stores gradient values for each tensor where gradients are activated. Now, this is an important line where gradients are activated. We'll see what it means in a little while. Because you can create tensors where you don't need to essentially where the gradient isn't calculated simply because you don't need it to be calculated. So you can essentially not have that gradient in your memory, and the gradient calculation doesn't need to take place. So just show how it works. So we'll create a torch.1 5. we're going to make requires grad to here. I'm going to copy a loss function here because it's a pretty long function and to sort of see what it does. So binary cross on entropy with logits is is a loss function commonly used when we need to classify between multiple classes. You can use other as well. You can use a sigmoid or another classification function as well, but we'll be using this one, so it doesn't really make a difference. And so the concept here is that this is your expected input or your input. This is your expected output. And .matml x comma w. So this is your matrix, and this is going to. So you'll be able to visualize this in a second because we'll be using something. Now, y dot gradient underscore fn. So gradient underscore fn shows you the gradient calculation that has taken place on any given tensor. So now if I run z dot grad underscore fn, you'll see that there has been a gradient calculation on this, which has taken place here because there is a loss that has been calculated between z and y, which means that that was a gradient calculated between z and y. So essentially, grad underscore fn shows you whether or not there was a calculation that was done for a tensor with respect to another gradient for a gradient, right? Now dot backward. So if I have to,
Can you please again explain what was y dot grad fn?
so grad fn essentially shows you what gradient calculation was done on a given tensor. Now, as you can see, y wasn't operated on, so there was no gradient calculation that was done here. For z, there was a matrix multiplication and a bias added, which means that there was a gradient calculation done here. So there is a gradient associated to this. That's all. There was no calculation done here. That's why this y dot grad fn is empty. That's it.
Like, what is gradient?
Gradient is like the slope, right? When you if I had to look at it in an ND space, the gradient
Okay,
is the slope between two vectors.
okay, sir, got it.
Yeah, like the same gradient that we were calculating. So if you remember m1, the delta function, not delta, the a reverse triangle. I don't remember what it's called, but that's also a gradient if you remember the
Yes,
course.
sir.
Okay, so loss dot backward. So dot backward is a function that computes the gradients with respect to its parameters. In this case, for loss, as we've seen here, the function is the uh, objective function which has the parameters as weights w. So the w tensor that I've created here are the weights, and the b is the bias. The weight, w stands for weight, b stands for bias, And z is essentially a function which has x as its inputs, w as its weights, and b as its bias. Therefore, um, the parameters that this loss function has are w and b, because these are the weights and this is the bias. And it's going to be creating, and it will be calculating the loss between x, which are which is essentially the result of this transformation, and the output that we've created, which is y. Any questions here? The way you can figure out what the output z is like simple matrix calculation. So 5 times a matrix 5 by 3 will give you 5 times 1, 5 times 3 will give you a 1 times 3, which is what you need. The loss dot backward will essentially give you, okay, I also need to show it. Yeah. So you can also see what the loss was here. Yeah, we'll have to do a little work here for retain. Now the reason why this is throwing an error, and why I'm not going to be using this further because I haven't solved this error before, is because we have gone through the same calculation twice, which means loss will be calculated twice. So it's throwing an error, which is that you shouldn't be doing that multiple times, because the tensors are already saved and you'll be calculating loss again on an already on a gradient that's been computed before. Which means that the gradient values will change. So it's essentially saying that it won't give you the correct answer. So it's more a warning than an error, but it still won't allow you to do it. So we'll just instead show the gradient which have been calculated for the weight and the bias. So as you can see, a 5,3 matrix will have 5,3, like the gradients will be along this. The reason why these are the same is an exercise for you. You can go through, like, just you can manually go through this and see what calculations have been done, and you'll be able to figure out what. So if I give you like values of random, you will be able to do this by hand. It's not a difficult task. One sec. Right. So now an interesting thing. So what I had mentioned here. So where gradients are activated or where tensors will be able to use gradients is an important line, right? So when I do torch dot matmul is matrix multiplication. I haven't specified this, but this is standard matrix multiplication. It's the same as using an add function. Can also be done using a or w at b. So as you can see, this will requires not required. This will require gradients because there is a matrix calculation that is happening here. Now, if I use something called with torch dot no grad, which is essentially that it will not be using computing gradients for any part of this calculation. And I do torch dot matmul. W plus b, and I see whether it will require a grad again. This will throw a false. The reason being that this has been calculated, or this calculation has taken place where in a setting where gradients cannot be calculated, which means that you cannot go backward. So backward propagation, something that you probably have covered in class, says that for any backprop to take place, you need to have computed gradients, or at least you will be computing. You have to have computed gradients, and you will be updating said gradients on the backward pass, right? Here, because you have computed no gradient, z dot backward will throw an error because element 0 of tensors does not require gradient, does not have a gradient function. So you cannot possibly run a backward pass on a tensor that does not have gradient already computed for it. Okay, now we're going to look at a little bit of visualization. So in case you need to install a library or a package which is not already installed on Colab, you need to use something called you need to like append the exclamation mark in front of the pip install. Pip install standard Python function. So Torchwiz is a visualization library that we'll be using. This will create a graph and like show you what functions have taken place where, what gradient calculations and what overall functions have taken place where. So as you can see, the 5,3, this is the weights matrix, and this is going to create a set of gradient calculations. What are these gradient calculations? Beyond the scope of the course, you don't really need to know this. The only thing you really need to know is that this is the final loss function which takes place, which is going to calculate your final loss. So since this is the loss, so the variable we've used here is loss. It's supposed to be calculating loss, and this is the last step that is going to take place before no further gradient calculations will take place. What these do and what these are beyond the scope of the code, don't need to know it. Okay, so if I needed to look at, so as we've seen here, right here there is going to be a x dot matmul x comma w plus b, after which it calculates loss. If you come here, this is calculating loss between z and y, and z is a function, z is being calculated between x, w, and b. So if I wanted to remove b from the gradient computation, I will essentially do dot detach. So b underscore det, b dot detach, which will detach the tensor b from all gradient calculations that take place further. So now when I do z equal to dot matmul and I write a detached loss, which is going to copy this again. And I run make underscore dot underscore det. Well, you will see that there is a difference in the graph here because there is no b, the three element tensor b which is taking place here. There is no calculations for that here. There is a difference between the two graphs, as you will be able to see. Okay, so next we're going to go into how we need to create our data set. So we'll be using something called MNIST, which is a very standard, very famous data set for basic image processing tasks. We'll be using this again in the next lab for where we'll be building CNNs. Here we're just doing it so that you have an idea of how to create your data set and how PyTorch like gives you a lot of ease while creating these. So MNIST data set. Torch Vision is another library which is again already loaded into Colab. And okay, so um, as most of you already probably know, when we're building any sort of network or doing any machine learning or deep learning task, we need to have two data sets. We can also have three. We can also have a validation set, but we need a minimum of two. We need a training set and a testing set. The training set essentially helps the network learn because it's labeled data, and it will learn after every either data point or every set of data points, something we call mini batches. Or and then during the testing set, it will essentially just calculate the error which is accumulated over a set of data points, so that it is able to see whether or not the model is actually functioning. So the train data set is labeled data, and there's only one difference in the model and post model creation. You'll see that there's only one difference between a training loop and a testing loop, and it's that the testing loop does not update the model because you don't have labels to see while you're testing. What are labels? The answers to the data point. So MNIST is a handwritten classification data set, where you will be classifying numbers, handwritten digits from 0 to 9 into their respective classes. So I created, so we'll load the training sets and testing sets. PyTorch gives you the option of like downloading them directly. It's very easy to do it here. But if you had to do them on your own for a different data set, you would probably be using something like a data loader, or have to do it manually. Slash. Okay, so here we'll be creating so if you look at the size of the data set, it's going to be pretty large, which we don't want because we want to be doing the lab like right now. So if you want to go back, so when you're doing this on your own, you can do this with all the elements in the data set, which are pretty large. It's got, I think, 70,000 images, which is a lot of images, right? And each image is 28 by 28, 784 pixels. So it'll take a lot of time to train there. So we'll be using only 2,000 images, where 1,000 for training and a 500 for testing and 500 for validation. What is a validation set? Similar to a testing set, except you do it immediately after training. No real difference there. It's just like a sanity check before you deploy a model of sorts. Testing and validation sets are nearly the same size. Here we're using 1,500, 500 because we want training to be faster. So we're using a smaller training set. Ideally, the split is generally 70-30 or 60-20-20. Or sorry, yeah, 60-20-20, where 60% of the net data set is used for training, 20 for testing, and 20 for validation. Now we'll be reshaping the images here to have only 784 columns, because the model that we're building today is a standard neural network, which cannot like look into spatial features, and unlike a convolutional network. So convolutional network will be using the image as is, or will be adding a padding layer to it, something you learn in the next class. But the model that we're building today is a standard linear fully connected network, which means that each input needs to be a 1D array. It cannot be a 2D array or a ND array. I hope that is clear. Now, what are targets? So the labels for each data. So I'll show you the I'll show you the image as well, and I'll show you the label for it as well. But a label is essentially the correct answer or the ground truths that we associate to each data point. So if a data point has like a certain answer that we expect, or the correct answer that we expect after training, that's essentially the label for it. Achha, right, my bad. This does not. So labels are already a 1D array. That doesn't make sense there. Now, just to like have a couple sanity checks with regards to what we're doing. So the length of the training set should be 1,000 data points. Otherwise, we have done something wrong. Similarly, like what is the type of the training set? It needs to be a PyTorch tensor. Otherwise again, we've done something wrong. So it is a tensor. So no issues there. We'll also look at the shape of the entire set. And it's 1,000 points. So it's 1,000 rows and 784 columns. So again, this is exactly what we need. So I'm not going to, yeah, that's just annoying. Okay, but what I will show you is how the how you can use matplotlib to create to essentially see the data that you're using, right? So otherwise it's a little abstract as to what we're doing here. So this is something you can find from the matplotlib documentation very easily. I'm just going to copy it from there. It's not something which is very difficult. So this is just the first element. So train underscore x0 is the first training set. Dot view 28, 28, which just means that we're converting it back from the flattened 1, 784 back to a 2D array or an image. We're going to leave it in grayscale, and the minimum value of the pixel and the maximum value of the pixel color is going to be 0 and 255. Again, this is kind of the way the dataset was designed, so there is no real issues with that. Now, this sort of looks like a 5, and just to make sure that we're correct with regards to what this means, we'll use train underscore y0, and this should give us 5. Otherwise, we've done something wrong, and it's 5, so we're correct there. And it just means that what we're seeing on the image is the actual output as well, so there are no issues there. So now we'll be building the model. I don't have an image for creating the model, but hopefully you'll be able to see how it should look in a little while. Okay, so from torch import nm. This is F is not capital here. Right, so we need to sort of look at what sort of model we want to create, right? So I'm going to share another screen. I hope my screen is visible again, and you should be able to see an image.
So,
Right. So for this image, is everyone able to see my cursor?
so
Yes.
Yeah. So as you can see, there are 3 parts here, right? There's an input layer, hidden layers, and an output layer. The more hidden layers you have, the more possible models you can create, because a neural network is essentially able to map more functions or more possible functions with the more parameters it has. Again, I think this is something you'll cover in your theory lectures. But for the purposes of model creation, you have to understand that the input layer has to be equal to the number of parameters that your input function has. So if my image has 784 values, my input layer needs to be 784, needs to have 784 neurons, so that each input value corresponds to a neuron of its own. Hidden layers don't need to have any specific values, or you can increase and decrease. This is called hyperparameter tuning. You'll see that for certain hidden layer values, your model will overfit very heavily, or if your hidden layers are too small or too constrictive, they'll underfit very heavily. And the output layers, and this applies to both number of layers and number of parameters in each layer, number of neurons in each layer. As for output layer, here they have only one, but it depends on what the function of your neural network is. If your neural network is a regression based network, it will have only one output, because only one output will be needed for each set of inputs. But if you have a classification based network, you need to see that you need to have 10 layers, or 10 neurons. So in our case, we have 10 outputs, which is 0 to 9, right? Each digit of the handwritten set. And each neuron will have a corresponding probability value associated to it, and the maximum probability value will be given will be set to be the output of the network. Here we're not using a single output, because otherwise we're expecting a regression to take place between 0 to 9, and the closest number will be given that. But the problem with that just ends up being that it's not very accurate, because regression tends to have higher variance than classification. Also, because it's a lot easier to create a 10 output and then just have probabilities associated to it. Loss functions are also designed that way for classification. So so you need to essentially make sure that the output layer has a certain number of needs to be the number of classes that you're classifying to. Okay, is my collab visible again?
Yes, sir.
Right. So now we'll be building our network or our model, and we'll be doing this as a class. I hope we're all familiar with classes in PyTorch, like just classes in general.
Hello, sir.
Oh yeah.
Sir, how to choose the optimal number of hidden layers?
Something which will be covered in theory lectures, but essentially you need to worry about the number of parameters. Now, the general rule is that the number of parameters should be about 10 times the number of data points that you have. That's a rule of thumb. matlab, you can sort of consider that to be an approximation, and you can look at how the number of parameters are being affected by the number of layers and the number of neurons in each layer. But hyperparameter tuning is something that you can like look into on your own. Here we're just building a simple MLP, which is I think we can make either one layer or two layers depending on what we want to do here. But in general, worrying about the number of parameters is more important than just the number of layers and the number of neurons in each layer.
Okay, sir.
Okay, so the number of features and the number hidden number outputs. Number of features, as we've said, has to be 784 as we've defined earlier because um, the number of inputs for each image are 784, and the number of hidden is a hyper parameter in our network. So we need to essentially look at different values for this. There is something called Bayesian optimization, again not within the point of this course, where you can sort of look at what are the most optimal hyperparameter values, and you can use Bayesian optimization to find the optimal hyperparameter network without having to grid search across like a variety of hyperparameters. Um, and the number of output, as we've seen, has to be the number of classes that we're classifying to, in this case 10. Okay, so here we're going to be creating self.lin1, which is our first linear layer, right? And it has to be the number of input layers, number of input features, number of hidden neurons. Now, what is a linear layer? Coming back to this example, I hope my screen is visible again.
Yes, sir.
Yeah.
Yeah. So the green, so on the cursor you can see, so this is an example of a linear layer which will have some inputs and will have some outputs. So nn dot linear essentially defines the number of neurons, the number of input features, and the number of output features, the number of neurons and the number of in the next layer. And between each, like after each fully connected part, you need to have an activation function. So we'll be using ReLU, which is probably the most common activation function there around. You can use others as well depending on the purpose of your task. I think you'll learn about activation functions again in the theory sessions. So Now, another important thing to make sure is that between each layer, so if I had to create one more layer here, right? So let's say I create another layer, self.act1 is again NN.ReLU. The next layer that I create in T will have to have the same number here for its input. Otherwise, we're having different number of outputs for the previous layer and a different number of inputs for the previous layer, which doesn't make sense, right? Because then you're it just doesn't make sense for any sort of network to take place that way. Okay, so we're not doing this, so that doesn't matter. But right, so here we're also going to be looking at something called Xavier initialization. Not something you need to understand, but a good way to visualize how a model works is sort of along the lines of that there is an initial gradient, a random gradient creation or a random weight creation. For each neuron, there is a weight associated to it, and initially those weights are random. Um, Over the course of training our network, we sort of converge to a value where these weights are not random anymore and are sort of defined for or sort of represent a function that represents our data as closely as possible. Research says that if you use something called Xavier initialization, which I think initializes the weights over some distribution, results show that it converges faster because it's easier to represent a function that way. I'm not very sure of the theory myself. I don't think again, theory not relevant to the course, but in case you needed to but in case you like need to make a network, it's just good to initialize using Xavier. I'm going to copy the function directly here. Write a comment. Xavier initialization for weights helps model converge faster. And this needs to be done for both layers. So there's self.lin1.weight and self.lin2.weight. And we'll define a forward function. So this is for our forward pass over our network. So defines our forward pass for our network. And here we essentially need to just like go through every part of our network. So self.lin1 x x is now self.act, which is essentially doing the ReLU function on it, and then we again fill into. And this should not throw us any errors because we've just defined the class. Weirdly slow running. Okay, so by the time that runs, we'll just like go to the next part. So here we'll be creating an instance of the classifier model that we've defined right here, and we'll give it values, right? So the number of features we want are 784. That's the number of input features, not something we're defining on our own. Number of hidden features, we can come up with any value which like doesn't really make a difference. Here we'll use 512 just because again, no reason. You can play around with the value. It's actually a good idea to play around with the value and see how it affects your model and your model training. And just to see what the model looks like, we'll see. It's taking longer than usual. I think that's because Colab is run on a cloud instance and not on our local machine. So sometimes Google
Aryan,
decides that it'll take you longer.
I think the indentation is wrong on the forward function.
Uh, As far as I remember, I've set indentation to 2 instead of 4. 1 sec.
Not that way. I think the def is not aligned with the def in it. Def forward is
Ah,
set.
right. My
Yeah.
bad.
Cool.
Maybe that's why it's taking longer. Thank you for that. Let me just restart all them. Take a minute or so to run through. Sorry about this. Yeah, now it's correct. So here you'll be able to see that you have like 2 layers and a ReLU function between them. So now we'll look at training. So you can again run a couple sanity checks here if you'd like to, where you can simply run it on just randomized data. So you can create data on a normal distribution, set everything ahead of one standard deviation, one positive standard deviation to be 1, and label everything as to be 0, and see how the model fits to it. And if you have, and this should be able to perfectly represent that, so you will probably get like close to 100% accuracy on that network. So you'll be able to see how the network is training, and it will train perfectly because no, not perfectly obviously, but close to perfectly in that situation. Now here what we're going to be doing is normalizing inputs. Now normalization is essentially a process where we take all our values and place them between 0 and 1. Now because here all our values are between 0 and 255, we just have to divide by 255 to get them to be between 0 and 1. That's all we have to do. That same thing goes for the validation set. Okay. Now we'll be looking at something called batch size and the number of epochs. So batch size is the number of data points, or in this case, the number of images that your model will run before a single gradient update takes place. So I hope everybody should be familiar with backpropagation to a certain degree. And backpropagation is the process by which your weights are updated by gradient descent, or or using whatever you'd like, Adam optimizer or gradient descent. And in that case, what happens is that if you do it after every data point, it takes up a lot of memory and it takes up a lot of training time. Instead, you can sort of just do it after a certain set of data points. So after every 50 points or so, you can you can update your gradients backwards, and it'll take up less memory, but it'll also be less accurate because your gradients here are being accumulated instead of an update taking place after every data point. So here we'll set batch size again to 100. Let's just do it there. And the number of epochs to be, I think we'll do 10. We'll go with 200 epochs. Okay. Ideally longer. The number of batches per training epoch has to be the one sec. Right. So we'll print both values and see. So you have 1,000 images, right? And you have a batch size of 100. So for each epoch, you need to have 10 batches, right? For every image to be covered in one epoch. So one epoch is every single data point being covered or being learned by your model once. So if you have 1,000 images and a batch size of 100, which means a gradient update takes place after every 100 images, you need 10 batches for a single epoch to be completed. Does that make sense? Just to be clear, this will be 10 because this is 1,000 by 100. That's all. Import dot optim. Okay, so we're now going to be defining a class, an accuracy function. So this is pretty straightforward because it's and target. So predictions are the results that your model has created, and targets are the ground truths that we consider. Ground truth as in the labels that are present for the data that we have. And the accuracy is pretty straightforward. It's the number of correct answers by total number of answers. For IDX in range length. If it's IDX target IDX and the accuracy is by length 100 for the percentage. So I hope we're all clear up until here. So after this is so up until here we've just looked at basic PyTorch things. After and model creation. After this we'll be looking at creating a training loop and a testing loop. So we'll start by defining an optimizer first. Here we're using stochastic gradient descent. You can use Adam optimizer or any other optimizer if you'd like. For our example, it shouldn't make that big of a difference. but certain optimizers can help converge faster because of some reasons. Again, not really important. LR is your learning rate. So your learning rate essentially defines how how much your gradients can be updated by. So if you look at the function for gradient descent, you'll see that the update part of your, so when it updates by a certain amount each time, or by the strength of your updation, if you want to think of it that way. It's a slightly vague term, but essentially the larger your learning rate is, the larger the magnitude of your weight change will take place at every step. In some ways, this can be a good thing because this means your model can train faster and converge faster. But the problem is that for higher learning rates, sometimes it converges. Your model will converge to a suboptimal minima or a suboptimal loss minima, which means that it will have higher losses after it converges, because once it converges, it's very difficult for it to come out of that valley, or valley, if you want to look at error that way. And the loss function that we'll be using, criterion, which is your loss function, and n dot cross entropy loss. Again, cross entropy loss is a very standard function for multi-class classification problems. You can use others as well. Doesn't it will impact your model slightly, but again, you can just look into which ones would be better for your specific use case. Here, cross entropy loss works well. So we'll just start by defining a few basic things here. Epoch loss, losses at each point. Accuracy. And test accuracy. Validation accuracy. Now, when you think about how your training needs to take place, right? You can sort of think of it as, first you have a forward pass. So your model will generate an inference, which is, it will give you an answer for your given for a given data point based on initially its randomized weights. Then it sees how much its weights are wrong by, and it will sort of generate a it will see how much what error is there using your criterion, which here is cross entropy loss. Then it will compute a backward pass. So based on the amount of error that was present for the initial forward pass, it will see how much updation or what magnitude of updation needs to take place for the weights using gradient descent. It will then go backwards and compute a backward pass or back propagation. After that, it will and then that's after that it's like your weight update. So forward pass, error calculation, and backward pass. So for epoch in range, number of epochs, your initial epoch loss will be 0, and you need to shift your model to a model.train part. There's a difference between model.train and model.test. In model.train, things like skip connections and batch normalization are activated. In model.test, they are not. During testing, as you may have remembered earlier, we had looked at with torch dot with no grad, right? Which essentially means that there will be no gradient calculation or no gradient computation for all the steps that take place there. During testing, there are no backward gradient calculations then you need to do. The weights have essentially been set. So if I come back here, you'll be able to see what I mean. Yeah, here. So with torch or no grad, the weights are already like perfectly, are not perfectly set, but um, have been trained to whatever amount we need them to be trained. And once that's done, you don't need further back propagation to take place, which means you don't need further gradient calculations to take place. So you can essentially use with torch no grad there as well. Now for training one epoch. So for batch underscore IDX. Uh, the reason why we've sort of left variables like this is because this is also going to be the lab sheet that will be shared with tomorrow, this collab file, with some additional exercises. So you can actually go through this exact code and play around with it and see what values are working better for you. So if you want to change the number of parameters in your hidden layer, you can do that directly without having to worry about code that is like, not very easily changeable. Okay, so optimizer.zeroGrad. Now this is a very important part of the code that we're writing. Now, optimizer.zeroGrad essentially sets all the gradients for the optimizer to zero. And an optimizer essentially creates a matrix of all the gradients that it will need. Why do you have to set it to zero? Because optimizers, the way the function's been written in PyTorch in the backend is that it will accumulate all gradients unless set to zero. Why it accumulates all gradients? Because sometimes we want gradients to be accumulated so that we can average and then update our model in one go, instead of having to do it every time. So it really depends on how you want to sort of do your uh, weight updations. In our case, we want to do it after every loop, so we're doing that. The way we've written, the way I'm writing code right now is um, sort of allows me to do optimizer.zero grad. Otherwise, during mini batch training or batch training, you might have to have an if statement which after every 10 iterations, your optimizer will then go to zero grad and then you can make your weight updation before you set it to zero. Does this make sense?
So can you explain it once again?
Okay. So your optimizer, in this case, stochastic gradient descent, accumulates gradients. So it will compute a matrix of gradients, right? And it does not set them to zero after every set of after every batch or a training epoch is completed. It will simply continue to accumulate gradients. It will expand the matrix, or it will add the previous gradients to the current matrix. Right? Now we don't want that to happen, because then our gradients are the previous batch's gradients and the current batch of gradients by 2, which is bad because that's not the correct gradient updation that we needed to do. So that's why we set it to 0 here. During mini batch training or batch training, if you are not sort of doing it, so the way we've written the code allows us, I'll write the code, then you'll see what I mean. But the way we've written our code allows us to set the optimizer to 0 or the gradients to 0 at the start of each loop. Otherwise, sometimes you might have to, it depends on the way you're writing your code. It's better to try it out on your own. You might have to set optimizer to 0 after every 10 iterations of your loop, depending on how you write your code. So we'll create an input set, which is times batch size, which goes to Okay, so here essentially what we're doing is we're creating an input tensor, which is for the images. So each image, so this is like the first dimension, right? So okay, I'll just show it here so that it's easier to visualize. I'll just directly write this. I put in a value. You can visualize it. So here essentially what's happening is that you have your train function, sorry, your train tensor, which is all the images, right? 1,000 images times 784 pixels per image, and we're going batch by batch. So because we have 1,000 images training set and we have a batch size of 100, we need to go for 10 batches, right? Make sense?
Yes.
Yeah. And so 1 to 10 is essentially what we're doing, right? Number of batches per training epoch. In one epoch, we need 10 batches. As you can see, this will show you 10 if I hover over it properly. Okay, it's 10, but right. So this is essentially just creating the tensor, which is just that set of 100 images. Target underscore out are the labels for those 100 images. This is pretty much it. There's nothing else here. And output is the inferences that model is generating for this input set. Inferences are the output. So once the model has a forward pass, the output of that forward pass is this model input. Okay. Now batch loss. So the loss for this specific batch is going to be criterion, which is our loss function, output, comma target. Underscore out. All right. So output is what our model has generated. Target underscore out is the ground truth, the correct answer that our model should have generated if it was perfect. Okay. And now that we know this, we need to calculate loss. We've already calculated loss. We need to have backward prop now. So batch underscore dot backwards and optimizer dot step. Now we calculate epoch loss, which is for our entire epoch, which is epoch loss plus batch loss. Now, the loss on each batch will contribute to the epoch loss because one epoch consists of 10 batches. Each batch loss has, like, the contribution of each batch loss will contribute to that. And loss at each epoch. Yeah, losses at each point. Instead of writing point, I'll write epoch. That makes more sense. Point is weird. And this is going to be dot append. Epoch underscore loss by batch size. So here, once we run this, there might be a couple problems here because epoch underscore loss is a tensor that has gradient computation still attached to it. If you remember, we used a detach function earlier, which essentially removes this from all gradient computation. We want to do this here so that in case there are any gradient computations further because of like poorly written code or just general, sometimes there are just issues. We don't want this to change because of any gradient computation, or we don't want this to affect any gradient computation in the future. Now model.eval. So now we're switching to an evaluation perspective. So here in model.eval, as I mentioned previously, a lot of things like batch normalization, skip connections, stop taking place because now that you're testing, it should go through the entire model. And skip connections and things like that, which you learn in your theory classes, are supposed to help with training and to prevent things like gradient vanishing or gradient explosion. and other aspects of things like that. So this stops all of those from taking place so that it trains to the entire model the way it's supposed to. So train underscore threads. This train underscore apples. And now what we're doing is essentially similar, except we're not calculating, except we're not updating weights again. So the difference between this part of the code, I'll just like the difference between this and this is that we're not updating our model now. The model has learned whatever it's supposed to, and now all it's doing is like generating inferences and checking how well it has trained. If it hasn't trained well, we sort of have to figure out how we can make it train better. We can do that by like increasing our data set, changing our hyperparameters, looking at whether the model is overfit or not, or whether it's overfitting or underfitting. If it's underfitting, there are things you can do. If it's overfitting, there are things you can do. Maybe change our model slightly, introduce things like batch normalization if it's not working, regularization. A lot of things you'll be learning in your theory classes. So again, here. So here we can train throughout. So for batch underscore IDX. And this remains exactly the same. Yeah. Now, as I had mentioned previously, when I showed you the photo, the prediction of your model is going to be the maximum probability value, which is in the last output layer, right? So in the image that I showed you, there was only one output. If I had to show you an image with multiple, I'll show you that again. I hope you can see my screen.
Yes.
Yeah. So as you can see, the last layer here has 3 neurons as its output, which means that it's classifying to 3 classes. Now, which class is it actually classifying to? The neuron which has the maximum value associated to it. So let's say the first neuron has a probability of 0.6, the next two are 0.2 and 0.2. That means that this is the neuron that it's classifying to, or this is the class that it's classifying to, which means that this is the output or this is the prediction of the model. So here we're essentially doing something pretty straightforward. We're doing torch.argmax, which takes the maximum argument value, just like the maximum value. Output command name equal to 1, which is along the row. So then this is our prediction now. And train underscore threads. Just a sec. Why are we doing 2 numpy? Because it doesn't convert to a list, because tensors don't convert to a list directly. You sort of have to go through the numpy route. I think there is a function that lets you do it as well, You can look into that. I don't remember it, and like taking to going through documentation takes a little time. Right. So this is going to be the part where we've created, like, this is going to create our predictions and the targets for our testing part. Now we're going to create a validation set also. It's nearly the exact same thing. I think it is exactly the same thing. Just copy the whole thing. Except for train, we'll now just put val. Yeah, this is right. So now we want to get our training accuracies. So now it's getting accuracy. So we had defined a function for this earlier, def get accuracy. Here we're just using that to get our accuracies. So train for accuracies dot append. Um, right, train by distinct targets. And we'll just print out the loss for each epoch. So if for every 10 epochs, of mod 10 equal to 0. Now, why are we using -1 here? It's because -1 is essentially the last element of the array. So 0 is the first, -1 sort of wraps around to the last. So you don't have to worry about like placing the correct epoch value each time. And this should be correct. Let me just check it once more to make sure that I haven't made any mistake. Doesn't look like it, I hope. So let's sort of see if it's pairing properly. It is not. Okay. Yeah, I don't think we returned something here. Yeah, we're supposed to return X. Otherwise, it will not give us. It's just an error that I had made. Start again here. It will now work. Yeah, it's working. So as you can see, you can sort of see the loss and the accuracy at each point. I have a feeling accuracy is not being shown here properly because let me just check that. Right, so our accuracy shouldn't be this low, which means there is some error here, which I have to go through. Right, this is supposed to be dot start max. I'll explain this in a bit, but dot start max. Um, so it started by converging, which is weird. Oh, that's because it's converged here, so we need to start again. So as you can see, the model is sort of converging at a point and not changing, which means that um, at some point we've either made sort of a mistake with regard to the accuracies that we've created or the way that we're calculating them, or it's just converging badly. I set epoch loss to 0. Yes. Project step. Model.eval.
I think the validation predictions are not correct because you're taking the validation prediction from the training set.
Right.
Yeah, so the validation accuracy will change.
Yeah. That makes sense. I think this looks correct, right? Test underscore x, test underscore y. Let me just check that. Yeah. We just go back to our get accuracy function. I have a feeling we have done something wrong there. Okay, right. So this is an MLP, so we can't really expect great accuracy on this. Uh, but yeah, this is essentially the code for this. I don't think this is wrong as far as I can tell. Okay, yeah, this is already conversion to static. Wow, this is surprisingly worse. But yeah, essentially, this is sort of how your code is supposed to look like with regards to the model creation and the model testing loops. I hope this is clear. We'll share you the lab sheet tomorrow. So in case there's any error in the code here, that will be rectified. It doesn't seem like there's an error. I think this is just the model underfitting really badly because we've got pretty low data and not really a lot of epochs. We're also using batch training, which means that the updates are happening after every 100 or so things, which sort of means that the accuracy is supposed to be low. Um, just because it can train fast. I mean, if it's training in like 20 seconds, it's not going to do very well. Uh, Other than that, you can go through the matplotlib uh, library and sort of see how that's working, and you can plot your train and test losses. We've put them in an array here, so you can sort of plot them and see how it's coming about. You can also increase the number of epochs, leave this to train for longer, not use batch sizes. That will obviously improve accuracy over time. Increasing the number of epochs will just do that to begin with. Other than that, are there any questions?